Welcome back to the deep dive. Today, we're going deep on this paper that kind of shook things up in the machine learning world, explaining and harnessing adversarial examples. It's by Goodfellow, Shlens, and Szegedy.
Yeah.
And, as a data science, machine learning models, they can be crazy powerful.
Oh, yeah.
But this paper, it's like it pulls back the curtain and shows this surprising weakness. These adversarial examples, we're talking about inputs, and they're made to like trick these models.
Yeah.
You can even make a really accurate model mess up, like misclassify an image.
Right.
And it's just a tiny change you wouldn't even notice.
Yeah. And what's really interesting is that it's not because these models are super complex, which is what a lot of people thought at first.
Right.
But it's actually because they're linear.
That's a big shift in thinking.
Yeah.
So this paper is saying that like these high-dimensional spaces, which are like everywhere in machine learning, they actually make these tiny changes bigger. So linear models are really sensitive to them.
Yeah.
And they use this cool analogy, accidental steganography.
Right.
Can you sort of break that down for us?
So think about it this way. A linear model, it's really focused on signals that line up with its weights, the ones it learned.
Okay.
It's so focused that it can actually miss other important stuff in the input. So it's kind of like hiding a message in plain sight.
Okay.
These adversarial things, these little changes, they use that linear nature to make the model misclassify things.
Oh, I see. That's a really good way to picture it. And what's even crazier is how easy it is to make these adversarial examples. The paper talks about this fast gradient sign method.
Yeah.
It uses backpropagation to get the gradient, so it's not hard to do, and it's cheap.
And it works really well. When they tested it, error rates went way up, sometimes almost 90% on these standard data sets like MNIST and SciFar 10.
Right.
So that means even a slightly messed up picture, let's say of a panda, could be misclassified as something totally different, like a gibbon.
Oh, wow.
And that's a big deal, right?
Yeah.
Especially now that we're using these models for all sorts of important stuff in the real world.
Totally. Okay, so we know how to make these adversarial examples, but what can we do about it? The paper talks about adversarial training.
Yeah.
It's like fighting fire with fire, right?
Exactly. When you train on a mix of regular examples and these adversarial ones,
Right.
you're basically making the model learn the data better. It's like a way to regularize it.
Ooh.
So it can generalize better and not get tricked by these little changes.
And they got good results with that, right?
Oh, yeah. They saw the error rates go down a lot on MNIST. Sometimes it actually did better than dropout. And what's really cool is that these adversarially trained models, their weights are more localized and interpretable.
Oh, interesting.
So adversarial training might not just make them tougher, but also easier to understand.
So it's like making them stronger and smarter at the same time.
Yeah.
Now, the paper goes on to compare these linear units with RBF units.
Yeah.
And they frame it as this precision recall trade-off. Can you tell us more about that?
Sure. So linear units, they aim for high recall, meaning they respond to a lot of different inputs. But that also makes them easy to fool with these adversarial examples, so their precision is lower.
Ah, so it's trade-off.
RBF units, they're more picky about what they respond to. So they have higher precision, but they might miss some stuff and have lower recall.
So you're trying to find that balance, right?
Right.
Where it can detect lots of stuff, but also not get tricked too easily. And this trade-off becomes even more important with these adversarial examples, I guess.
Exactly. The kind of units you use and the whole structure of the model really affects how vulnerable it is to these attacks.
Okay. One of the weirdest things about this whole thing is how these adversarial examples can transfer. How can something designed to fool one model also fool others?
Well, the paper says it's because neural networks, when they're trained the usual way, they tend to learn similar functions.
Oh,
Even if their structures are different.
So they end up having similar weaknesses.
Yeah, these blind spots that those carefully made inputs can exploit. It's almost like they're accidentally helping each other out by showing each other their weaknesses.
That's a really good way to put it.
They tested this by making adversarial examples for one model.
Right.
And then trying them out on others like maxout, softmax, even RBF networks. It was really consistent. All these different models got fooled in similar ways.
Wow, that's both really cool and a little creepy. It seems like these adversarial examples, there's something fundamental about them that goes beyond just one specific model.
Yeah, exactly. And it makes you think about machine learning in a whole new way.
Right.
How do we build models that are really robust, that can handle stuff they haven't seen before, and not get tricked by these attacks?
Yeah.
I think we're just starting to understand these weaknesses and what they mean.
Okay, so the paper also dives into this other interesting idea, these rubbish class examples.
Right.
These are inputs that don't really belong to any category.
Right.
But linear models can be really sure about classifying them.
Exactly.
So even if the input is basically meaningless, the model thinks it's something real, which is kind of scary if you're using these models for important decisions.
It is. And it all comes back to how linear these models are. Because they can give these extreme predictions, even for data that's far from what they were trained on, they're really open to these rubbish inputs. They actually suggest a way to make these fooling images that target specific classes
How do they do that?
by adding a gradient step to Gaussian noise.
It seems like we're always trying to stay ahead of these adversarial attacks.
We are.
But this research, it gives us a way to understand these weaknesses and make better models.
Exactly. And that's where things get even more interesting. Let's dig more into the solutions they came up with and talk about the bigger implications of these adversarial examples in the next part of our deep dive.
Sounds good.
Welcome back. Before we go on, I think we got to highlight something that people don't always think about.
Okay.
Like the size of the input space we're talking about here.
Right.
It's mind-boggling. Even these huge data sets, they're just a tiny, tiny part of all the possible inputs.
So you're saying even if a model's doing amazing on a data set,
Yeah.
it could still act weird when it sees something totally new outside of those examples.
Exactly. What this paper is showing is that a model being able to fit the training data doesn't mean it actually understands the task.
Right.
It might be picking up on these random correlations or like little statistical quirks,
Yeah.
but not getting the real idea behind it. So in a way, these adversarial examples, they're like showing us those cracks in the model's understanding.
It's like the model learned the dance moves, but then you change the music,
Right.
and it's totally lost.
That's a perfect analogy. And the paper, it goes into detail about how these weaknesses show up. Like, take these shallow linear models.
Okay.
They tend to give extreme predictions when the data is far from what they were trained on, so they're really vulnerable to those rubbish class examples.
So like a basic linear model sees a bunch of random pixels and says, oh yeah, I'm 90% sure that's a 5.
Exactly. And the paper compares that to RBF networks. They're different. RBF networks are more localized.
Right.
So when they see something way outside their training data, they're not so confident.
So they're basically saying, I have no clue what this is. I'm not going to pretend.
Right.
Which is, I guess, more honest.
Yeah, exactly. And this shows why it's important to understand model capacity. You might think that a low-capacity model, like a simple RBF network, wouldn't make many confident predictions, but that's not always true. Even a simple model can be overconfident, especially with these weird inputs.
So even if a model looks simple on the surface, there can still be all this hidden complexity and weaknesses. And this shows why we need really robust training methods.
Yeah.
Especially for models with high capacity, like those big neural networks.
Totally. Stuff like adversarial training is super important to make those models build up stronger internal representations.
Okay.
It's like you're stress testing them.
Right.
Showing them these tough examples and making them learn from their mistakes.
Got it. And what's cool is that adversarial training, it does more than just make them tougher, right? It also makes them more interpretable.
Yeah, that's a key point from the paper. It challenges the idea that just because a model can explain the training data, it really understands it.
Right.
Just getting good accuracy doesn't mean it's grasped the concepts.
So we got to watch out for models that are just mimicking patterns
Yeah.
without actually getting what they're doing.
Exactly. And adversarial examples are really useful for that. They're like probes.
Oh, okay.
Exposing the blind spots where the model doesn't really get it. Like they're pulling back the curtain on a performance that looks impressive,
Yeah.
but showing the shaky stuff underneath.
So we need better ways to evaluate these models.
Absolutely.
Not just looking at accuracy on a test set.
You need to test their understanding,
Right.
see if they can handle new situations and resist these attacks.
Yeah.
That's where adversarial training and analyzing those rubbish class examples come in. They give us tools to stress test our models, find their weak points. Right.
And make them understand things better.
So it's like, we're not just training models anymore, we're actually educating them, trying to make them understand the world in a deeper, more robust way.
That's a good way to put it.
Yeah.
This research on adversarial examples, it's a big step in that direction. It makes us question what we thought we knew, improve our training methods,
Yeah.
and really try to understand what it means for a machine to learn. The paper goes into some really interesting details about these vulnerabilities
Okay.
and how they show up in different types of models. It talks about the role of different activation functions, how effective ensembling is,
Yeah.
and even how generative models could help with robustness.
Interesting.
And it brings up some deep questions about optimization itself. Is it always a trade-off?
What do you mean?
Like easier to train, but less resistant to adversarial examples.
Mm-hmm.
This paper seems to say maybe. It encourages us to explore new model structures and ways of training that could maybe break that trade-off. So for everyone out there working in data science, what should they take away from this research on adversarial examples?
It's a wake-up call for all of us. We
Yeah.
need to stop just chasing accuracy and start prioritizing robustness. It's not enough for a model to do well on a nice, clean data set. We have to think about those unexpected inputs, the edge cases that might trip it up.
So always be on the lookout for those weaknesses.
Yeah, even in models that seem like they're doing great.
My God.
And this research gives us the tools to find those weaknesses. Adversarial training, like we talked about,
Right.
is a great way to force models to face their weaknesses and build stronger
It's
representations.
like putting them through boot camp.
Exactly. Make them ready for anything. And it's great that adversarial training often makes models easier to understand, too. That's really important,
Yeah.
especially when we're using AI in areas where trust and transparency matter.
So it's not just about making them tougher,
Right.
but also making sure we understand them and that they're accountable for their choices.
Totally. But adversarial training is just one part of the solution. We got to explore other ways to improve robustness,
Like what?
like coming up with model structures that are just naturally more robust, or finding ways to detect and stop these adversarial examples in real-world systems.
So it's a big challenge.
Yeah.
That needs a whole bunch of different solutions.
Exactly. And this paper, explaining and harnessing adversarial examples, it gives us a solid starting point.
Okay.
It helps us really understand why these adversarial examples exist
Right.
and how to make them. It gives us the knowledge to see them coming and deal with them.
So before we wrap up our deep dive on this groundbreaking paper, I got to ask one more question. It's kind of a philosophical one.
Okay, I'm listening.
If even our best models, the ones we think are the most advanced,
Right.
can be fooled so easily by these adversarial examples,
Yeah.
what does that say about our own human weaknesses?
It really makes you think. I mean, our brains are basically biological neural networks, right?
Yeah.
They learn and represent information in similar ways. So it makes you wonder, do we have blind spots too?
Yeah.
Like cognitive biases that could make us vulnerable to these adversarial things, just like those models.
That's a pretty wild thought. But let's get back to data science.
Okay.
You're the expert here building these powerful models. What are some practical things you can take away from this research?
It's a big shift for all of us. The main thing is we got to stop focusing only on accuracy and start really caring about robustness.
Right.
It's not enough for a model to just do well on a perfect data set. We have to think about those weird inputs, the edge cases that could throw it off.
So always be on the lookout for those weaknesses, even if the model looks great at first.
Exactly. And this research gives us tools to actually find those weaknesses. Adversarial training, like we talked about.
Yeah.
It's a great way to make models face their weaknesses head on and build up those stronger representations.
It's like giving them that hard training so they're ready for anything.
Yeah, exactly. And it's cool that adversarial training often makes those models easier to understand, too. That's so important.
Yeah.
Especially when we're using AI in areas where we need to trust it and understand what it's doing.
So it's not just about making them tough.
Right.
It's also about making sure we get them and that they're responsible for their decisions.
Exactly. But adversarial training, it's just one part of the solution. We have to look for other ways to make things more robust.
Like what?
Well, like designing model structures that are just naturally more robust, or finding ways to spot and stop these adversarial examples when those systems are actually being used.
So it's a big challenge, and we need a lot of different solutions.
Absolutely. And this paper, explaining and harnessing adversarial examples, it's a really solid place to start.
Okay.
It helps us understand why these adversarial examples exist and how to make them. It gives us the knowledge to anticipate and deal with these weaknesses.
So to wrap up our deep dive, let's go over the key takeaways one last time. Number one, a lot of machine learning models are vulnerable to these adversarial examples because they're linear. That makes them sensitive to those carefully designed changes.
Right.
Number two, adversarial training. It's a powerful way to make things more robust, and it often makes the models easier to understand too.
Yeah.
And finally, this research is a call to action for everyone in data science. We have to prioritize robustness as much as accuracy, make sure that the AI systems we build aren't just powerful, but also reliable, trustworthy, and good for society.
Well said. It's a really exciting time to be working in this field. We're pushing the limits of what's possible with AI, but we have to be aware of the potential problems. This paper is a great guide. It helps us navigate these new challenges and build a future where AI is both powerful and responsible.
Great. Well, thanks for joining us for this deep dive.
Yeah, thanks for having me.
We hope this exploration has given you some good insights, maybe even some new ideas for your own work in data science. Until next time, keep exploring, keep asking questions, and keep pushing the boundaries of what we know.